Okay, so the plan for today is to continue with chapter 10 on parametric equations. I think we're only going to get through 10.4 today, which is fine. We'll skip over 10.5 and 10.6. That I typically treat that as optional material anyway. It is, moderately interesting, but I think really the main ideas with parametric equations are covered in 10.1 through 10.4. And the quote of the day today is from the Stoic philosopher, the Roman Emperor Marcus Aurelius, and it's often just quoted as B1, and it comes from this line from his Meditations. Uh, one translation is "Stop arguing about what it means to be a good man, be one." Or in other words, it's kind of comfortable to sit here and debate philosophy, but actually going out into the world and bringing that to life in a sense is really where it's at. So, okay, so let's move on to 10.4 areas in polar coordinates. And we have a definition here. If r equals f of theta, we mentioned last time that we can think of polar functions, r as a function of theta, like this, r equals f of theta. If it is continuous and non-negative for theta in AB, where A to B spans a set of angles less than 2 pi apart, then the area is the integral from A to B of 1/2 f of theta squared d theta. This seems like it really just comes out of nowhere. Let's try to get an idea of uh, where this comes from. Okay, so first let's remember that if we have a circular segment of radius r, so for instance, I have this quarter circle of radius r, and if I have some circular segment, say this here, and I have some angle, let me actually call the angle delta theta. Then I have some area. So what's my area going to be? Well, it would be the area of the whole circle, which would be pi r squared, and then times will be delta theta, the amount of angle that I have that's sweeping out my area here for the sector, divided by the total angle all the way around will be 2 pi. Or I see my pi's go away and I get r squared over 2 delta theta. And I think we might already see where this is headed. So if I have, say, a function, let's just draw it in the first quadrant so that it's easier to think about. If I have a function r equals f of theta, I can imagine going from, say, theta equals a, in this case, theta equals 0 right along the x-axis, to theta equals b, and I can imagine looking at a bunch of really small increments in theta. I'm going to raise my theta equals a to b to make things a little easier to see. But I can imagine a lot of really small increments of theta, like this. And I'll take a bigger one here just to be able to have enough room to demonstrate it. But I'm imagining splitting up this domain, this theta sweep into a bunch of really small theta subintervals, the same way that we might split, say, an interval A to B on the x-axis into a bunch of subintervals to make Riemann boxes, we're going to do something similar here. So here I have an angle delta theta, and I can approximate r equals f of theta here by just, say, a constant function in r, a constant radius over this little slice here. So this area, say a sub I, well, the area, the red area is, what would it be? It would be r sub I squared over 2 delta theta. And then, of course, I want to add up a bunch of similar areas. So the overall, let's say that this whole black area here we'll call A. The overall area is approximately the sum I equals 1 to n of these A sub i's, or it's approximately 1/2 r I squared delta theta. Or I can write that I equals 1 to n, and r equals f of theta. So this is like f of theta sub I squared delta theta. And then we let delta theta go to 0 and the number of slices go to infinity. And this goes to integral from a to b 1/2 f of theta squared d theta, which is exactly what we have up here. So really just coming right out of this, this little circular segment area over here. We just basically created Riemann boxes, but now they're kind of like Riemann slices almost. Okay, let's do a really a small problem, a small example. Find the area enclosed by the curve r equals 1 between the angles 0 and 2 pi. So this, of course, should just be the area of a circle of radius 1. R is just the constant function, 1. So f of theta equals 1 everywhere for all thetas between 0 and 2 pi. So my area then should be integral 0 to 2 pi. I notice that f of theta is non-negative everywhere. And I notice that the span of my angles is less than or equal to 2 pi. So from 0 to 2 pi. So it looks good. So I'm not like going around and tracing this out more than once or something like that. One thing that happens here, just a little side note, if we had Riemann boxes from say A to B and I have a certain area here, if I push B out a little bit further, well, I just get more of the function that I find the area under. That's a pretty reasonable thing to do. If I have r equals f of theta, and I'm looking for the area of this shape, well, if I keep incrementing theta more than 2 pi units, then I might start, I suppose it doesn't have to really meet up over here, but I might start doing something like this and accumulating kind of more area that I am not really sure what to do with. So what do I do with the overlap between kind of this green area and this black area? I've kind of already counted the black area. Do I want to recount it? Do I not want to recount it? What do I even mean by the area that I'm looking for at this point? So I might have to be more careful about what I'm discussing or asking for here. And if I was to use angles that went more than 2 pi, if I went more than one way all the way around, more than once all the way around, um, I'd have to be more clear about what exactly it is that I'm looking for. That would also cause a problem with signed area because, or we see a similar problem with signed area. Let's say that f of theta was positive for theta between 0 and pi, and then like negative for theta between 0 and 2 pi. So I have kind of like negative area here and like positive area there, and they kind of overlap in this region. What do I do there? Should they cancel each other out? Should they like add together? I'm not exactly sure. I also see that I am taking f of theta squared. So I kind of like naturally lose my sign information, right? Uh, so just kind of practically, that's why we want to check these conditions. And we do see that we have no problem with those here. R is non-negative everywhere, f of theta is non-negative everywhere, and we're going one time around, so we're good. And this is, of course, just uh, 1/2 times 1 squared d theta, or that's 1/2 times 2 pi minus 0, which is pi, the area of a circle of radius 1, as we'd expect. And just had Pi Day a couple of days ago, so this is a fitting topic, I suppose, to be discussing. All right, let's take a look at something a little more complicated. We have a curve here, r equals 3 cosine 3 theta. And I want to look for the area of one petal, so to speak, of this curve. It's not even super clear what I mean by the word petal. So let me change my screen share here. And let's take a look at the graph of r equals 3 cos 3 theta. So if I go to my y equals menu, and remember, if you're not in the polar coordinates mode, go to mode, and then down here, instead of function or parametric, go over to polar. And then this is obviously how you change it back for kind of normal plotting if you have another class that you're working on as well. But go over to polar, and when you go to y equals, you should have the polar menu, r1 equals, and when you type in your general variable, it should be theta instead of x or t. Okay, let's clear that out. And we want to type in 3 cos 3 theta. So 3 cosine 3 times my variable. My general variable button will pop in a theta for me, because that's the appropriate variable here. I'll close my parentheses. I know that cosine is between 0 and 1, the outputs. So 3 times cosine of stuff is between -3 and 3. I also know that, well, cosine is 2 pi periodic. If I took my interval from 0 to 2 pi, then 3 theta is going to be like 0 to 6 pi. I'm probably going to end up going around a bunch of times. I think I can get away with just going from 0 to like 2 pi over 3. And I'll keep my theta step at this, roughly 0.1 value here. This is just what the calculator by default sets it to, but if yours is different, just change it to 0.1 or so. And then I think my outputs from 3 times cosine of something are going to be between 3 and -3. So let me go x min to -3, x max to +3, and the same for the y's. And now I'll graph. I think I made oh yeah, I did make a mental flub here. I want to go from 0 to, to 2 pi. There was, I want to go from 0 to 2 pi on theta. Let me regraph that. Okay, now we get all the way around. Let me change the zoom up so that it's square so I can get a little better perspective on what's happening. So zoom 5 squares it up. And I see I have this kind of like, almost like flower with 3 leaves. And that's actually what this 3 theta is giving me. Those 3 leaves there. Let's make sure that we're going around exactly once. Let me go back to my y equals menu. And if I see when I'm on like the 3 times cosine or whatever, I can navigate back and forward with my arrow keys. If I go one more to the left, I see that my equal sign is flashing. If I were to like hit enter and move off of that, I can see that it's now unselected and the calculator won't graph this function. So if you had several functions in here and you wanted to graph one but not the others, you could turn them on or off that way. Let me go back to the equal sign and turn this one on. Okay, that's bolded now, so it is on. But if I go one more to the left, I'll see that actually all the way to the left, these slashes will also flash. So I can actually change the type of graph that the calculator is going to graph for me. Now, one downside of this just kind of normal default line graph is I saw that if I went from 0 to 2 pi, it graphs this curve. What if I go from 0 to say 4 pi? Well, other than seeing that it's still calculating and still doing something for a while, it actually looks exactly the same. I don't know if I've traced out this curve, once or twice or 5 times. Let me go to my window and go back, say 0 to 2 pi. And here I'm going to go to my y equals menu, go left to the equal sign, left one more so that that slash is flashing. And I can hit enter and that would plot it as a bold line. If I had maybe 2 functions, I wanted to be able to tell them apart. Maybe I plot one as a normal line and one as a bold. If I hit enter again, I actually get this kind of a thing. It's like a dash with a open circle next to it. And that's what I'm going to use. So I'm going to use the one that's like a dash with a circle. What this will do is it'll show a visible circle on the graph, and that circle will trace out exactly where it's almost like the point of the pencil that it's drawing, but it'll also leave behind a line. So if I graph, and pay close attention when I graph because it will go by kind of fast. So if you're ready, I'm going to hit graph and then pay attention and watch the little thing go around. Here we go. Okay, I actually see that it went around twice. It traced out the whole figure twice. So on 0 to 2 pi, traces out the whole figure twice. Let's try 0 to pi then. So I changed my theta max to just pi. And now let's check. I do see the whole figure traced out. And then my little like pencil point kind of stops. So I see that I get something like this. Oh, I really missed on that going through the origin there. So I get something like this from t equals 0 to t equals pi. And something I notice is that cosine is going to start out positive, and then, so this is where cosine is positive, and then it's going to turn negative. Oops, it's going to turn negative. and then positive, and then actually negative again. So this is like this section down here is coming from the angles over here where cosine is negative. So that's a little bit annoying. So maybe instead of looking for, so I'm looking to isolate one of these leaves. I'm looking for something like this area. This is the area that I want, or these petals, right? This is what I'm looking for. But here I have kind of like one component where cosine is positive, another where it's negative. They're also split apart. It's like from 0 to something, these should be thetas. But it's like 0 to something and then something to pi. But one thing I might be able to do is go from maybe say like negative pi over 2, over 2, to positive pi over 2. We graph that and see what that looks like. That's looking a little better, right? So I could also think of this as being like, this is always going to be theta equals 0 out here. But if I go from, say, negative pi over 2 to positive pi over 2 on my angles, I'm actually going to get cosine, get the contribution from cosine being positive in both of these halves of the petal to the right here. And now I just need to figure out what is my range of angles that will trace out just this first petal here. And we might guess it's going to be negative pi over 6 to pi over 6. So we try negative pi over 6. Whoops. Pi over 6. There we go. And that looks just about right. Right, notice that negative pi over 2 to pi over 2 traces out 3 petals. It traces out the whole thing once. So then a third of that should trace out 1 petal. I'm looking at the interval negative pi over 6 to pi over 6, and I verified with the calculator that that does indeed just trace out this 1 petal. Okay, so what do I want then? I want my area to be integral negative pi over 6 to pi over 6, 1/2 f of theta squared. D theta. Or this gives me 9/2. I do note that my interval is symmetric. It's even. My interval is symmetric and my function is symmetric. My function is even. So I can actually double the value of this integral and integrate from 0 to pi over 6. I actually might have even been able to leverage that symmetry earlier and realized that on my original go around when I was just integrating from, or just tracing from theta going from 0 to pi. So I might have been able to use that kind of geometric symmetry between the positive y part of this petal and the negative y part of this petal to even, make this leap a little earlier. So we have 9/2 of the constants coming out from the 3 squared and the 2 times 2, integrating an even function over a symmetric interval is double the interval from 0 to b of that function. So that 2 comes out. And then I have cos squared of 3 theta d theta. My 2's go away. And since time is rapidly disappearing, I will skip the details and we end up with 3 pi divided by 4. But the main thing I wanted you to see was, using a bit of our knowledge and understanding of trig functions and also a bit of help from the calculator actually made this process pretty quick. We didn't have to do a ton of trig or a ton of algebra, and we didn't have to do a ton of just kind of blind poking around in the calculator. We're using the two hand in hand, right? The calculator gave me an idea. I, it wasn't quite what I wanted, so I shifted. I tried something else on the calculator that looked a little bit better. I got another guess, this may be negative pi over 6 to pi over 6. I went back to the calculator to verify that. So going back and forth between the knowledge and intuition and algebra and the calculator helps me generate ideas or confirm, and my intuition about the trig functions and how they work and all of that, the two work nicely hand in hand. So I don't like to think of using the calculator as a crutch, but really using it as a tool that really helps my understanding. It really helps me to display my understanding better, right? Saves me some of the busy work and lets me do more of the thinking work and leave more of the busy work to the tool. Okay, so let's take a look at this problem. It's kind of a challenging problem. Find the area between the outer and inner loops of r equals 1 minus 2 sine theta. Oh, calculator just shut off. There we go. So let's come back here and graph out 1 minus 2 sine theta. And again, just so that we know how many times we're tracing this out over a given interval, let's change our trace type to the one with the little circle that leaves the line behind it. And then when we graph, we can just pay close attention and see how many times that circle goes around so we don't mistakenly trace out the whole figure a couple of times. So let me think about, I'm going to come off to the side here for an aside. So the xy graph of r equals 1 minus 2 sine theta, here I have x and y, and then I have theta and r. But I just want to get an idea of how r relates to theta. So I'm actually going to come over here and look at theta and r like this, right? Just r is a function of theta, where theta is my horizontal axis and r the vertical axis. This is an aside because I'm just trying to get an idea, like, is r going to go negative? When might r go negative? Things like that. Okay, so let's start building this up. What does sine theta look like? Sine theta looks like that. 2 sine theta just looks like this. And negative 2 sine theta, well, let me delete this. Nice. Negative 2 sine theta just looks like this. Overshot a little there. There we go. And what's 1 minus 2 sine theta? That's negative 2 sine theta plus 1. So we're just shifting this whole thing up 1. So I do think that r is going to go negative a bit. It's going to probably be mostly positive. It's going to start out positive for positive thetas, or for slightly positive thetas. It's going to go negative a bit, and then it's going to come back positive and actually come up to be pretty positive, up to a maximum of 3. So when sine theta is -1, I'm going to get 1 plus 2 or 3. So my radius r is going to be between, well, r is going to have an upper bound of 3 and a lower bound, well, actually -1. So some r's are going to be negative, some positive. But let's just start off by getting an idea of what this is going to look like. Also, this is 2 pi periodic. Let me let theta go from 0 to 2 pi. Again, my theta step, if yours is some wonky number, just set it to 0.1 or so. And I think I'm just going to go from -3 to 3 on both axes. I should be able to get everything in the picture then. My y min and max are already set to -3 to 3. Let me graph this. And then maybe I'll do like a zoom square, zoom 5. It kind of looks like I can come in a little bit on the horizontal axis, maybe also on the vertical axis. So let me make y go from -3 to 1 and x maybe from like -1 to +1. Let's see if that's too aggressive. And what did I say? -3 to 1 or so on y. Oh, there's a little bit too aggressive there on the x-axis. That's fine. We'll just go -2 to 2. Yeah, that's a little better. Okay, so I see that I get in this land over here, the land of the kind of actual graph. So remember, this is an aside. This is not what the this is not what the graph actually looks like. This is a polar curve like this one over here. So I see I have, let me draw them in even different colors. I have one regime over here. This is this little green bit here where theta is a little bit positive and r is positive. And then I have, maybe I'll switch to red. I have this regime where r is negative for a little bit. And then I have this bit here where r comes back positive again. So r is positive in the green area and the blue area, and negative in the red area. Okay, now I kind of clearly see what the outer and inner loops are. The outer loop is the one consisting of kind of the green and blue traces. There's an area between it and the origin. And then there's an area in the red loop, like inside of the red loop. And I want the area between them. So really, I want the kind of green-blue area. What's the whole area inside of this like entire envelope of this picture, minus the red area. It's kind of what I want to do. All right, well, let's think of our intervals here. So for the green area, theta goes between 0 and something. For the red, theta is between, maybe I'll call this theta 1. It's between 0 and theta 1. For red, theta goes between theta 1 and theta 2. And for blue, theta is from theta 2 to 2 pi. And I see that I want to do something like I want to do something like integral 0 to theta 1, some stuff, minus integral theta 1 to theta 2 of some stuff, plus integral theta 2 to theta 3 of some stuff. And actually, really, the stuff is going to be the same in all of them because what I'm going to be integrating is r squared, or f of theta squared. The sign is going to go away. The sign, the plus or minus sign, is going to go away. So I really am going to have the same integrand in all of these. I might actually see that I can maybe make things a little bit simpler by, instead of going from 0 to 2 pi, I could actually start at theta 1. I could start here, go around my red loop. That's the integral from theta 1 to theta 2. That's the red area. I could bring that area in with a negative, and then to that I could add going all the way around and back to the beginning of the red loop. This would actually be what, from theta 2 up to 2 pi plus theta 1. Would bring me all the way back to the red loop. Going from theta 1 to 2 pi plus theta 1 still is a span of 2 pi radians that I'm going around. I'm just choosing my start and end points a little differently so that it makes the integrals a little bit easier. I don't think there's really anything wrong with doing it the first way. It's just that I have to do a bunch more evaluations. Might be easier to do it this way. Okay, so now I have a plan of attack. And I need to figure out, and just to be clear, to fill in some details here, these integrands are 1/2 r squared d theta for both of them. This negative here that we put in manually takes care of the kind of between the curves, meaning subtract off the area from the red curve, or the area in the red curve, subtract that area from the area inside the blue curve. This r squared is squaring off any effect of the r being negative here. All right, so now really what I need to do is I need to find an indefinite integral for 1/2 r squared d theta. 1/2, and then what's r squared? 1 minus 2 sine theta squared. D theta. So I need to figure out this indefinite integral. I also have to figure out theta 1 and theta 2. I need to figure out when is this thing 0. So this is thing number 1 I need to do, and thing number 2 I need to do is figure out when is r equals 0. That gives me theta 1 and theta 2, and then I can just plug in, get my answer. All right, so this is, so I get 1/2 times 1 squared. My, be careful with this 1 minus 2 sine theta squared. It's a binomial squared, so I have cross terms. I have a minus 2 sine theta times 1, minus another 2 sine theta times 1. So that's minus 4 sine thetas over 2 is minus 2 sine theta. And then my last gives me plus 4 sine squared theta d theta. And again, because we're running a bit short of time, I'm going to leave the details of this integral as an exercise. We covered trig integrals in chapter 7. So this -2 sine theta will integrate easily. The sine squared theta, use an identity for that. And we end up with, what do we end up with? There we go. We end up with that. And I'm not going to put a plus c on here because we're only intending to use this indefinite integrals. If that irks you, you can feel free to put a plus c on there. So I'm going to want to evaluate these two integrals from theta 1 to theta 2, or theta 2 to 2 pi plus theta 1. And then when is r 0? Well, that's when 1 minus 2 sine theta equals 0. Well, that's when sine theta is 1/2. I know that I'm going to get a quadrant 1 and quadrant 2 solution to this. So theta 1 is going to be my quadrant 1 solution, and theta 2 my quadrant 2 solution. All right, so when is sine theta 1/2? Well, I know that I have a situation here where my opposite is 1 and my hypotenuse is 2. That sounds an awful lot like a 1, 2, √3 triangle. And I know this is a 30, 60, 90 triangle. So my 90 is there. My smaller angle, 30 degrees, is opposite the 1. 30 degrees is 1/6 of 180, so that's pi over 6. And then my 60-degree angle is going to be 2 pi over 6, double that 30-degree angle, or it's going to be pi over 3. And I know that sine is opposite of hypotenuse, so it must be that sine of pi over 6 is 1/2. So theta equals pi over 6. That's my, what is the name of it just escaped me, the terminology for it, but my reference angle. And then I place one of those in the first quadrant, of course, giving me theta 1 is pi over 6. And I place one of those in the second quadrant because sine is positive when y is positive. That's in the second quadrant. This gives me theta 2 is pi minus pi over 6 by pi over 6. Now, fingers and toes crossed, if we take theta from pi over 6 for theta min up to theta max of 5 pi over 6, we should only see the smaller inner loop, the red loop traced out. And that's exactly what we see. So again, using our calculator to check our work, this looks good. All right, and what is my answer? I'm just going to call this big F of theta. So my area that I'm looking for is negative big F at 5 pi over 6. So negative of big F at theta 2 minus big F at theta 1, which is negative big F at 5 pi over 6, plus big F at pi over 6. That's from the first integral, plus big F at 2 pi plus pi over 6. But I know that r is 2 pi periodic. So that's really just big F at pi over 6. the same as 2 pi plus pi over 6 in this context. And then minus theta 2, 5 pi over 6. All right. And that is my solution. I can combine these two together. I can combine these two together. So I end up with double something. That does kind of make sense because this is nice and symmetric about the y-axis. I kind of have a left half area doubled to make the right half area. But I would do this simplification with these two evaluations of big F here. And that's my answer. So it was a decent bit of work, but again, I think especially in these polar curves, this is, polar curves and really a lot of our work with trig is where going back and forth between kind of the calculator and intuition and algebra and working on the working things out manually. I think that's really where you see the really nice balance between using the calculator as a tool, but also using it to further your intuition rather than just kind of take everything over. Okay, and then let's look at this last problem on points of intersection. So let's try to find the points of intersection of these two curves, r equals 1 minus 2 cos theta and r equals 1. Well, r equals 1, not too bad of a curve, just a circle of radius 1. Circle of radius 1. And this, r equals 1 minus 2 cos theta. Cosine is basically just like sine, but shifted 90 degrees. This looks a lot like this picture. It should look like this curve here, just kind of rotated 90 degrees. So this should look something like that. Oh, back into the origin. There we go. Now we might say, okay, if I was in Cartesian world, I am somewhat, I suppose, but if I was thinking in Cartesian coordinates, if I had y equals f of x and y equals g of x, and I wanted to find points of intersection of these two curves, I would set f of x equal g of x and solve for x. Well, we can do that here, right? So 1 minus 2 cos theta equals 1. R equals 1 minus 2 cos theta, R equals 1. We'll set 1 minus 2 cos theta equal to 1. And what do I see? I see that negative 2 cos theta equals 0. Well, that means cos theta has to be 0, which means theta equals pi over 2 or 3 pi over 2. So I think those are my two intersections for these two curves. Let's plot these on the calculator and kind of make sure. All right, so what do I want? I want 1 minus 2 cos theta. And again, I'll change both of these to that circle plus leaving a line behind option. I suppose r equals 1, I don't really need to change that. I know that's going to look like a circle of radius 1, but I'll do it anyway. I go to my window and I'll go from 0 to 2 pi. I see both of these are 2 pi periodic. Again, if your theta step was something wonky, just put 0.1 or so in there. And then I think my x min is going to be like right? So for my previous function that looked similar to this, but just rotated 90 degrees, the kind of x and y were interchanged. I had x from -2 to 2 and y from -3 to 1. I'm just going to swap those. X go from -3 to 1. And if I make a mistake, I can come back and change this. Y going from -2 to 2. Then let's graph. That's looking good so far. And there's my circle. Let me zoom square. I'll zoom 5. So my circle looks a little more like a circle. Let me screen cap this really quickly here so I can draw on it. And I do see my 2 points of intersection that I identified here and there. Theta equals pi over 2, theta equals 3 pi over 2. Interestingly, I actually see what looks like a third point of intersection. So what's actually happening here? Well, if I set R1 equal to R2, what I'm saying is, okay, when I have this theta, or well, when I have this theta, this is R1, this is R2, so +1 and negative maybe, 2/3 or something like that. Those aren't the same thing. When I have this theta, R1 equals 1, R2 equals 1, those are the same thing for theta equals pi over 2. When I have this theta equals pi, from the circle, R is 1, and well, from the circle, R equals 1, and oh, I think I have the wrong one here. From the circle, R equals 1. So let me write this over here. Theta equals pi, circle, R equals 1, and the, what should I call this? Cardioid. The cardioid, R equals, what was it? 3. Was it 3? Yeah, 3. So it looks like not a solution there either. Let me erase these. It's trying to draw too much on the calculator screen. But when theta equals 0, the circle R equals 1, and the cardioid R equals -1. So I see that when theta is 0, my circle point is out here, my cardioid point is back here, and I get blue to show up on here. When theta equals pi, my cardioid point is actually at this, or sorry, my circle point is here, and my cardioid point is here. So my circle point and my cardioid point, they do cover the same XY coordinate, but at two different values of theta. So when theta is pi, the circles R equals 1, that's the point x comma y equals -1 comma 0. And when theta equals 0, my cardioid point is R equals -1. That's the point xy equals -1 comma 0. So we have an interesting question here. If we were modeling this as like two planetary bodies going around or something like that with, say, parameter t being like time, would they ever collide? Would they ever be like in the same place at the same time or like the same place at the same angle? Well, the answer would be no. They, they would collide here and here, but here, would they collide there? The answer would be no. But like if I had an observer sitting here in space, would they be able to interact with body one at some point and then body two at a later point at that same point? That's the same point in space. And the answer there is yes. Both trajectories go through -1, 0, but not for the same angle, right? The circle goes through it when the angle is pi, and the cardioid goes through when the angle is 0. So because r could be positive or negative, I actually need to treat this like an absolute value. So I have r1 equal r2. That gives me some solutions. And then when could r1 be negative r2? That's going to give me some other solutions. And realistically, these are actually only going to give me potential solutions. I should really check and make sure that these actually are solutions. So when is 1 minus 2 cos theta equals -1, when r1 equals negative r2, I subtract 1 over, multiply by -1, 2 cos theta equals 2, or cos theta equals 1. And cos theta is 1 when theta is 0. So I see that one of my, when theta is 0, for my circle, r equals 1, or my cardioid, r equals -1. And then I have to check so I also have a solution. When I check my theta equals 0 against theta equals pi, 180 degrees, opposite of one another, I have my third solution. The two curves do intersect whenever theta is 0 as well. So they intersect at the points x comma y equals 0 comma 1, 0 comma -1, and at the points x comma y equals -1 comma 0. So I need to treat these kind of questions a little bit more like absolute value equations, right? Set R1 equal to R2 to find potential some potential solutions, and then R1 equal to -R2 to find other maybe potential solutions. And then, I think probably double checking on the calculator is the best way to go about it. I suppose you could kind of brute force it like I did over here. But I think I think this is a place where using the calculator as a tool is much more helpful than trying to reverse engineer the whole problem and figure out where all of these intersections lie. The calculator gives us some pretty darn good hints, and then we can build off of that. But we do see our third solution coming out algebraically if we force the issue. All right, any questions on parametric equations? All right, so like I mentioned at the beginning of class today, we will skip over 10.5 and 10.6. That's kind of optional material. And next time we will start into chapter 11. Chapter 11 is a monstrous chapter. I think we'll be in chapter 11 for the better part of a month or so for something like 8 class meetings. So covers sequences and series, and it's really the last major topic in Calc 2. After that, we touch on chapter 12 a little bit on three-dimensional space, but that's almost like a bridge into Calc 3. And then we pick up with three-dimensional space and all of that fun stuff, multidimensional spaces in Calc 3. But really, Chapter 11 is where we're going to be for most of the rest of the semester. So I would recommend taking a glance through the first couple of sections on sequences and series, maybe before next class, and then actually maybe taking a glance through that material before the following class as well, just because Chapter 11 does become a bit more complex, a bit more technical, and it is one of the more challenging chapters in the course. So take a look through that material, take a glance through it before next class. Let me stop the recording.